Hello and welcome back. In this video we'll be learning about implicit differentiation. To begin with, we should review a little bit of what our notation is for taking the derivative. If I have some function f of x, I can take the derivative of f of x and I can call it f prime, the prime meaning that we've taken a derivative, or I can use this d by dx notation. I think this is called the Leibniz Notation. And if we're graphing our function, we normally represent that our function on the y-axis. So here, y is just going to be some function of x, and when I take its derivative, I can either write y prime, or I can write dy dx. And this is the derivative with respect to x. It could be that maybe my function is going to be a function of t, and I could write y as a function of t, or I could use up other variables. So for instance, if I have, didn't write my t here correctly, if I have p of t, maybe I'm looking at a population over time, and I call it p for population. If I take its derivative, I would have p prime, and I would write d by dt of p of t. So the variable on the bottom is what we're taking the derivative with respect to. So here I'm taking the derivative with respect to t. Up here I'm taking the derivative with respect to x. But in any way, it works exactly the same as you would expect. So let's look at the next couple of questions. So let's find the derivative if y is equal to the square root of x. Well, let's find the derivative of y if y squared is equal to x. And when we look at these, there isn't a whole lot of difference. Here y is equal to the square root of x, and here y squared is equal to x. Well, if I go up here and I square both sides, I'll see that y squared is equal to the square root of x. There is a subtle difference if we were to try to graph these. Here, if y is equal to the square root of x, we get something that looks like this. And then stops there because we can't take the derivative of negative numbers. So this is what this graph looks like. However, over here, there's a very subtle difference, because now if y squared is equal to x, that means that y could be the positive square root of x, or y could be the negative square root of x. So we actually get something that looks like this. So this isn't a function. It doesn't pass the vertical line test. It crosses two places. But this could still come up in some situation. I could have y squared is equal to x, and I just have two different solutions for the y value. Just a sideways parabola. So the question is, how do we find the derivatives? Well, up here, this is pretty straightforward. If I have y is equal to the square root of x, well, then I can just take the derivative and the derivative of y is going to be the derivative of this side. And with the power rule, I bring down the power and I raise x to the 1 fewer power. So this is going to be 1/2 x to the negative 1/2. And this absolutely works. But one thing I want to point out is essentially what I've done is I've taken the derivative of both the left and the right hand side. Whatever we do to one side, we have to do to the other. So on the left hand side, I just get the derivative of y, which is exactly what I wanted to solve in the first place. On the right hand side, I had to take the derivative of that function, which we have our simple power rule. If I want to take the derivative of y over here, well, it's going to be a little bit more messy, but not quite. What I'm going to do is I'm going to write the same equation down, and whatever I do to one side, I have to do to the other. So I want the derivative, right? So I'm going to take the derivative of both the left and the right hand side. This is where things start to get interesting. The right hand side is pretty simple. The derivative of x with respect to x is just 1. That's pretty simple. We have a straight line, and its slope is always 1. Over here, I have the derivative with respect to x of y squared. Now, y itself is a function. So here's how this is going to work. I have y squared. So if I take the derivative of anything to a power, I'm going to bring down that power, raise it to the one less power, which is just 1, so I can just get y to the first power. But I have to chain rule, and I have to take this times the derivative of the inside. The inside is y itself. So I have to take this times dy dx. So this is chain rule. If we think about this a little bit more, what's going on here? I have y squared, and again, what I can do is I can kind of think of this as y is a lot like a function here. So this is going to be f of x squared. And how does the chain rule work here? Well, if I want to take the derivative, I move the 2 down, I plug my function back in, and then I take this times the derivative of the inside. So again, if I have y squared, I bring down the 2, I raise it to the 1 less power, and then I take it times the derivative of the inside, which happens to be dy dx. But I want to find dy dx. This is what I want to solve for. Well, then it's just a matter of solving this for dy dx. So then, if I solve for that, I just divide both sides by 2y, and I get dy dx is equal to 1 over 2y. There is my answer. The derivative of y with respect to x, when it satisfies this equation, is 1 over 2y. Now, I could try to solve for y here and plug that back in, but it's unnecessary. I know what the derivative of y is with respect to x. It's going to be 1 divided by 2y. And if I pick a point along here, I know the y value, I know the x value, and I can simply plug them in if I want to find the derivative. And that's pretty simple. Let's do another example, because I think more examples of implicit differentiation is best. So let's use implicit differentiation, forgot the L, to find dy dx. If 3 times x times y plus 7 is equal to 0. So this is a function that off the top of my head, I wouldn't know what this function looks like, as in I wouldn't be able to plot x and y very easily. So let's use implicit differentiation. So again, implicit differentiation, we're just going to take the derivative of both sides. Whatever you do to one side, you have to do to the other. So I'm going to take the derivative of 3xy plus 7, and that's going to be equal to the derivative of 0. Well, again, this right-hand side, the derivative of a constant, say 0, is just 0. And then I have the derivative of this left-hand side. And I'm gonna take my time with this. So the derivative of two things being added together is just going to be the derivative of the thing on the left, plus the derivative of the thing on the right. So again, when we differentiate things being added together, we just take the derivative of the first one plus the derivative of the second one. Okay, so that's pretty straightforward. Now let's look at the derivative of this left-hand guy. So I've got 3 times x times y. Well, first of all, I can pull out the 3, because any a constant multiple I can pull out of the derivative. And then this guy, the derivative of 7 is just a constant number, it doesn't change, so its slope is 0. And we get this. Okay, so if I add 0 to something, it doesn't matter, so I'm just going to pretend like I didn't write that down. And I have 3 times the derivative of xy. So I have the product rule here, right? I'm going to take the derivative of x times y plus the derivative of y times x. So again, I have two things being multiplied together. I'll take the derivative of the first one times the second, plus the derivative of the second one times the first. Take both derivatives and take them times the other function. And now we can really start to simplify, and everything is going to sort of fall into place. I'll have 3 times the derivative of x with respect to x. The line y equals x has slope 1, so that's just 1, times y. So 1 times y, that's y. The derivative of y with respect to x, well, I can't really simplify that. That's just the derivative of y with respect to x. And all that is times x, and that's equal to 0. So what have we done here? So to go from here to here, we use the product rule. And then this last one, we just started taking the actual derivatives. And then what I'll do is I'll divide both sides by 3. And then I will solve for dy dx. So here, dy dx. I will move the y to the other side, and I'll divide everything by x. Sometimes my y's and x's look similar, so I apologize. And this is our answer. Again, I move y to the other side, so I have a minus y. And then I divide both sides by x. And that's it. Now, we did a lot of this work. I showed a lot of steps here. You wouldn't necessarily have to show this many steps. I was just going through it and being careful. There is one other way to solve this that doesn't use implicit differentiation, which I will just mention because I think the implicit differentiation actually works a little bit smoother. So here, I could just solve for y. So if I have 3xy plus 7 is equal to 0, that means 3xy is equal to negative 7, or y is equal to negative 7 over 7. Negative 7 divided by 3x. And then I could take the derivative of both sides and in order to find dy dx. When it says use implicit differentiation, they usually mean don't solve for y. Don't try to solve for y, because there are situations in which you can't solve for y, and we need to use implicit differentiation. So for example, in this equation here, it is impossible, well, I don't want to say impossible, but it would be extremely difficult to try to solve for y and then take the derivative. We will use implicit differentiation to find the derivative of this guy, and I will do that in the next video.